Hello, welcome to this innovation coffee break focusing on the electrical power system simulation package. To give you an overview, we will present the workflow and the features in respect to the bidirectional DC-DC converter demo. This demo was already presented in the previous coffee break, but here we have a short introduction. So here we can see a mild hybrid car with a starter generator. And we have here two batteries, so the 12-volt battery and the 48-volt battery, and they are both connected with a DC-DC converter. And on the next slide, we can see the topology of this circuit. So we have two buck boost stages, named here with phase 1 and phase 2. And on the left and on the right, we have the batteries. Both are modeled by an idle voltage source and an additional resistance. And this schematic can directly use an EPSS to initiate a simulation. And how this is done in detail will be described by my colleague Katrin.
Thank you, Axel. Here you can see the same topology modeled with SimScape Electrical Specialized Power Systems. The EPSS package allows an easy way to compute this model directly on a DSpace FPGA board. EPSS consists of two different parts, a processor-based approach and an FPGA-based approach. In this video, we focus on the FPGA-based approach. We've highlighted the DSpace blocks in light blue here. An important block is a setup block, which contains all the configuration for your model. So you can select the FPGA board on which you want to run your simulation, then configure the sample time for your model. You can choose minimum here. Then the minimum possible sample time is automatically computed, or define a custom one. You can select the solver type and the number of output iterations, which is important to consider diodes correctly. On the tab circuit parameterization, you can enable scenarios. Scenarios give you the opportunity to switch between different parameterizations of your model during runtime. In case of the bidirectional DC-DC converter, there are different modi, and these can be realized by varying some parameters, that is, R high and R low. So here, the list is given where all the possible parameters that you can vary are shown, and we can choose R high and R low here. Then we can configure the scenarios and define what happens. So one can simply add a new scenario here, and then give it a name, and type down which parameter values are desired here. We have pre-configured this here for the demo, and for example, you have the buck voltage control mode, a boost voltage control mode, and so on. Having done these settings, you can use the Analyze Model block to find out if your model is ready for FPGA use. So here, you can generate an HTML file with detailed information about your model. The results for this example are shown here. Here you can see that the minimum step size is less than 1 microsecond, and the FPGA compatibility check says that your model is ready for EPSS file generation. But what does this mean? Well, an EPSS file is the container we use to collect all the data from your model, and it can be generated via the setup block. So here you find this tab export SimScape electrical model to EPSS file. Having done this for your model, the next step is to use the product configuration desk. There is a configuration desk plugin for EPSS. So you just start, create a new project, and then go to the signal chain view. In the function view here, you find the entry electrical power system simulation with an EPSS or an FPGA block. This block has to be dragged to the functions part here, and then you choose the EPSS file, and it is configured for your application. So what you have to do next is to configure where your gates and I/O comes from. For example, the switch gates, do they come from processor, from digital in, or something else? Where do the inputs come from can be easily configured here, and also the outputs. Then this block here is generated automatically, and you can connect the hardware. This can be done just by going here to the hardware button, then import hardware, replace, and choose the hardware you want to use. We also need a connection to a processor model, which has to be placed here. This can be done quite easy by right-clicking our EPSS on FPGA board, extend signal chain, and create suitable model port blocks. Then all the necessary blocks are created, which then can be used as an analog in a Simulink model, which can be connected here in the model parts. After having done all the configuration, just simply click the Start button here, which starts the configuration desk build. This build is not time-consuming because it does not include an FPGA synthesis, but it includes pre-configured FPGA builds we have directly included in EPSS. So it typically takes just a few seconds or only a very few minutes. The next step is to observe your results. For that, we use the software control desk. As you have already seen in the demo presentations, there are special control desk instruments for EPSS, like the FPGA scope. EPSS is also well suited for larger topologies. To demonstrate this, we have extended the demo by 2 additional phases you can see here. In this case, we end up with 16 switching elements, because the MOSFETs consist of an ideal switch and a diode each. To simulate this, it's quite challenging because you have 2 to the power of 16 state space representations, which you cannot compute. That is more than 65,000, and that for each scenario. But in many cases, different additional assumptions can be made for your model. In this case, we could choose as an example that no short circuits occur. So then the setup block gives you the opportunity to exclude switch combinations. This is the exclude switch combinations GUI. You can easily configure the switch combinations you want to exclude here. We have prepared it here for the model such that no short circuits occur. So for example, here high side and low side ideal switch are not allowed to be on at the same time. This is excluded, and you can vary here different combinations you want to exclude. Another possibility to tune up your model is to use model splitting. This is our model splitting block, which you can configure. You can choose between different splitting methods and different types of connections. This model splitting block distributes the model mathematically into 2 parts. So it's connected via measurements and sources, and gives you the opportunity to compute much more on one FPGA board, or even to extend everything to multiple FPGA boards. To check if your splitting does not influence your model in a negative way, we have developed the Analyze Splitting block. This block gives you the opportunity to check if there are special dependencies between switches or between states in your model and highlight these dependencies. And also you can compute the stability for any possible switch combinations. So in this case, also an HTML file is generated. For our model, you see this file here. And here you can see, okay, if you choose the delay insertion methods, then none of your switch combinations is unstable. So in this case, this method is well suited for your model. There are several other features available in EPSS, like for example correction methods and a special GUI to configure inter-FPGA connections. So feel free to contact us. We will find the best solution for your specific application.
DSpace, your partner in simulation and validation.